So now that we've gone through a couple of examples of pointer syntax and how they act in memory, let's take a look at maybe some applications and some kind of issues/concerns with how things go together. All right. So one first idea. A lot of times when you have what's called a complex type or a compound type, people will use pointers, right? So maybe I've seen like an array, maybe I've seen like a struct. Structs are going to be covered in a later section. But when you have basically a big piece of data, right? Not something that's bigger than just an int or a float, right? Something that's bigger than just 32 bits, right? If you have something that's hundreds of bytes long, right? Well, what people tend to do is they oftentimes will use a pointer kind of to indicate it or to remember where it's being stored. So over here, right, I have two pointers. I have a pointer P and a pointer S. And these are pointer variables, right, to these strings. And these strings, right, are compound types or complex types. Well, they're in the end, I guess there's even simpler than that, right? They're really just arrays. But they have a lot of data in them, right? One has 6 characters. The other one has, 12 characters or something like that. It's a lot of data there. So people like to use pointers, right, when you have a lot of data that's being stored, in some place, right? So instead of just having, a kind of a fixed thing where you don't have a pointer at all, you use a pointer here. The reason for that is that you get kind of fast, well, there's a couple of reasons for that. Big reason, right, is for kind of fast copy times. So if I have a line like this, P equal S, basically what happens, right, is I'm saying, okay, I've got that P variable and I want to store whatever is in S into P. Well, if I didn't have pointers there, right, imagine if it was just kind of this monolithic thing where each of those variables just had all those letters in there, well, then I would need to go and copy each of those 12 characters one at a time from S, right, into P. And that's going to be a little bit slow. So a better idea, right, is say, okay, you know what? If P and S are just pointers, well, then all I need to do is copy the pointer over, right? And that's actually what the picture on the right-hand side is showing, right? Initially, S points at that stuff, P points at other stuff, right? But if I want to, instead of having to, manually copy, everything one by one, just kind of slow. Well, instead of that, I just do this, right? I add my pointer that says, okay, you know what? P is now knows about the address where S is keeping stuff, right? So it's basically one of the things it does, right, using pointers, one advantage is that you have kind of faster copy operations, right? People don't need to do a deep copy where they copy every byte inside of a piece of data. Really, you just, have, okay, I'm going to write down the address where the new thing is being stored. So it can speed up some operations, right? Especially when it's very heavyweight things, right? Array is pretty small, but when we get to structs, it's a lot of data to pass around. It's a lot easier to just pass around a pointer. The other reason why they use pointers is because pointers basically can serve as a starting place for something, right? So if I have, a variable that has, it's a compound type, there's, maybe multiple things in there, right? That's what we call a struct. It's a structure of data. Well, a pointer basically gives us a starting place, right? It says, okay, go somewhere in memory, and then, after that, at, +0, then +4, then +8, right? There's different things being stored, right? So it's like a pointer is also giving us a starting place, right? Instead of it saying that, oh, this variable, just contains that H or that T, right? In our examples here, what we're saying is, okay, that pointer is the address of where that thing starts, right? And then we can go and we can say, hey, I can look in memory and I can grab everything from that, everything in memory, right, from that H all the way to that /null, right, until I get to the end of the string. So the pointer there in that case has the advantage of basically saying, okay, this is where my data starts, right, instead of just saying, oh, it's just an H, right. If I need to store a lot of stuff, then I just want to be given, the address of where it is, and then I eventually can go there and take out whatever it is that I actually need. Moving along, we have the idea of 2D arrays in C. Right, so we've had 2D arrays before, right, in Java. Here they will be similar, but we'll have kind of one additional thing we can do. So looking at this little program here, first part is kind of familiar to us, right? An include, a main. And then over here, right, we're creating a pointer P and then a 2D array of type char. The 2D array will end up working pretty much like what we expect, right? We have kind of our 2 brackets, which indicates 2 indices, right? So up or rows and columns, right? Basically, what we'll have is first our columns first, and then our rows second. Excuse me, rows first, columns second. Yeah. So you can look down here, right, and basically this is us filling in that 2D array, right? So we're going into one space, each space, right, one at a time, right, putting in all of our letters, and at the very end we have that null terminator, just because. Okay, now if we think about how this looks in memory, well, in memory, right, even though I'm kind of drawing this out to say, okay, this is, something that's 2 by 4, right, that's a rectangle, can't look like that in memory, right? Somehow there has to be some mapping, right, where the stuff that I have that's in a matrix has to be linearized. And so the way that he's going to do that is what we have on the right-hand side, where we say that, okay, each row is stored one after another. So C uses what we call row major order, right? See, on top we have A, B, C, D, right? Our first kind of row, and then immediately after it, our second row, E, F, G, null. So that's kind of how that thing is going to be compacted down to memory. Now this is interesting to us because it actually gives us a new way to access data in that array. So what we can do, right, is we can say, okay, what if I, let's say, create this new variable, or assign this new variable at p equal ma? Well, ma is basically going to be the address of where that first thing in that array is being stored. Take that, right, store into p. So initially, right, if we do, star p, that'll give us back an a because, well, hey, that's the first thing that's stored there. Now, what happens, right, if I do, p++, right, or I move p along by 1? What happens? Well, p++ has the effect of moving p from being a pointer to a to p being a pointer to b. So initially, right, it starts over here. Our plus gets us over here. And so you can imagine you do plus again and again, right? First, the second time gets us to C, third time it gets us to D, fourth time actually gets us to E, right? So we're actually going to roll over and naturally start on that second row in the piece in the data that we have, right? So this is actually kind of nice because no longer do we have to worry. Well, this is nice, but I'll give you a caveat in a second. What's interesting, right, is that we can say, okay, I don't need to have nested loops to go through a 2D array. All I need to do is have one pointer that starts at the beginning, one loop, right, and that loop just pushes that pointer along, and it'll naturally touch every element in there until it gets to the very end, right, until we get to that null symbol. Oh, and by the way, this little bit of code here, we have well star p. That code there is having the effect of moving p forward, right? Well, has the effect of looping, moving forward, right? While p isn't null, right? The instant p returns kind of a null character, this statement here, right, or this conditional here will end up being false, and the whole thing will drop out, right? So this is kind of a way that we can loop through everything and then just quit out at the end, right? Because this while, right, this while statement, right, is going to continue while that conditional is true, and the conditional is written as star p. Well, star p is basically going to each space in that 2D array and looking up whatever is there, right? And that while is only going to, well, it's going to treat anything that's non-zero as being true. So when it looks up that A, it'll be fine because it's like a 65 or something like that. B, it'll be fine, some number, right? And those are all fine, right, up until the very end. It gets to the null, and then, okay, yeah, that's, 0. It'll end up exiting out, right, because that condition ends up being false. So that whole mechanism there, right, of basically starting at the beginning with this p equal ma, right, looping along it while you have stuff there, and then moving p up by 1. That's kind of a different mechanism, right, in order to go and look at every element in this 2D array. The code we have inside, right, this printf and this p star stuff, I guess as a quick note, this is some cheapo encryption is what I labeled it as. That printf, right, probably you can guess, it's basically printing out each character at a time, right? So the output on the screen would be A through G, right? But then that second line there, what that second line is doing, that star p equals star p plus 1, that's basically shifting over each letter by 1, right? Because the letters, right, in any kind of programming language, right, they typically correspond to an ASCII number, right? And so if we do plus 1, it's like saying, okay, A, I'm going to turn you into B because I'm changing the number that's being used to represent it. Or, you have B, right? B corresponds to some ASCII number. We do a plus 1, it moves it forward to C, right? And then that new number gets stored back into that variable. So whatever we have here, right, basically be shifted over, and all of a sudden, it would have B, C, D, E, F, G, H, right? That would be the concept of it because we're going to each variable or each position, right, and moving it over by 1. Last thing we do, right, is just do a printf with a blank line, right, to move down. So there we go, right, kind of an overview, right, of how multi-dimensional arrays are represented in memory, and also, right, this technique for being able to loop through them with only using one loop. The one FYI or one caveat here, right, is to me, I think it's a little bit more clear to have different loops because you can kind of see how each loop corresponds to dimensionality. In this case, we're just kind of flattening down everything, which is faster, but just kind of a little hard to read in my opinion. So the final thing I want to talk about is basically misuse of pointers, right? Or doing stuff that we definitely should not be doing. Let's think back to the idea of constants, right? So we had constants in Java. We had this keyword called final. Basically, the idea was for some variables or even classes, right, we want to make sure they stay the same, right? For a variable, right, where we did something like say, okay, maybe I have this value, right, and this value, right, I really don't want it to vary, right, I don't want to have a variable. Instead, what I want to have is a constant. So I'd create something that looks like a variable, right, but then I'd add on that modifier final, and what that meant is that nowhere in that class could anybody change the value that was stored in that variable, right? It gets set up once and then left alone. So that's a constant. Well, we have constants in C too. So let's read through this program. and see what exactly is going on. So at the top, we have the usual code, our include and our main. And the first thing we have, right, is we have the definition of a constant, right? So this is the syntax we have in C if we want to create a variable that doesn't change, right? So I is a variable that'll be initialized to 5. And then from that point onwards, because it's tagged as constant in front, nobody else will be able to change it. Or we at least would hope nobody else would be able to change it, although we're going to do bad stuff with pointers in a second that'll let us change it. All right, but hopefully, right, the plan, right, if you were to using this in a program is you'd kind of be like, oh, I made this thing a constant, it should stay that way. Now, as a constant, one thing to be aware of is that that is actually still going to be a variable somewhere in memory, right? So basically what will happen is it'll still be something that gets allocated storage for, and your compiler basically will just be on the lookout to make sure you never do I equals something else, right? If you don't try to assign into it, you don't try to change it, right? Your compiler will be on the lookout for that. And if you ever actually do that, then your compiler will generate an error and say, okay, this is not okay. He's trying to update something that's marked as constant. I have an issue with that, right? So you get kind of this compile time protection for what ultimately will be compiled down into just another variable in memory. All right, so good so far. Looking down, int star j. Well, we can probably guess by now that's creating a variable called j that's going to be an integer pointer. All right, so if we had this line here, it's commented out, right? Imagine if I just had it there, right? I equal I plus 2. Well, maybe you can guess what would happen. It would give us a compiler error, right? It would say, okay, you can't change a constant, right? It would complain to us. So that line I'm leaving commented out because it's just not going to work. Because there, right, const is doing its job. Now consider, though, if we did the following. What if we said j equal and of I? Well, I is our constant. We're looking up the address of where that constant is being stored and then storing that address into j. So maybe not so bad yet, but a little bit questionable. Now, the next line, right, we have is our printf, and here, right, we're saying, okay, I'm going to print out the value of I, right? Well, initially, I is going to be 5, and because it's a constant, it's going to be, still that value, at least for now. So this will print out 5 over here. But then we get down into kind of dangerous territory where we go star j equals star j plus 2. Well, this, right, has the effect of looking up the value stored at the address that's in j. Well, the address stored there is the address of I, the constant. So this ends up being a 5 over here. Well, 5 plus 2, that gives me, 7 overall. And that 7 is going to be stored into star j. So actually what happens is that 7 will be stored into I. Even though I is marked as a constant, we're able to get around it by looking up the address of where that constant is being stored and then storing information into that address, right? Because the compiler isn't going to protect that address per se. What it's protecting is that, it's going to make sure you never do an assignment to I. Well, now, right, we have an indirect way of getting at the data that I knows about, and so then we can use that indirect way, right, that star j, to take that 7 and store it into I. And so now if I were to run this program, what I'll get back is, okay, there is now a 7 stored here in where I is, right? So that is kind of bad, right? This is, kind of a demonstration of, the power / dangers of pointers. So you're actually able to go and read stuff that you're not supposed to. Actually, right, even in... I'm thinking back to kind of years ago, right? You could do very bad things, right? Before there was kind of additional security in our operating systems, you could do things like, for example, look up the address of another program in memory, right? So something else could be running at the same time as your program, right? And you could actually look up, what was there, right, and maybe change something, right? There's actually a way you can use this to to get around things like, for example, private variables, because you can go and say, okay, let me grab the address of an object, right? And that object has some variables in there that are marked as private. Well, if I can, get the address of that object and find out the offset, to basically add a number to it, right, to get me to the address where the instance variables are stored, well, then I can go and I can change them, myself, right? Even if they're marked as private, I'll still be able to access them. I'll still be able to change stuff. So there are, some bad things you can do with pointers, right? Because they give you all of this flexibility. Constants, right? When we use that constant, keyword, we can kind of see, right? That was, basically just having a variable and having compile time, checks to make sure that nobody's, assigning into it. Other than that, right? It's still just an actual variable, right? It has memory allocated. We can figure out where the address is, right? We can make assignments into it. It's just a variable. It's protected during compile time. The other way we can actually get constants is by using something called macros. Macros, which we'll talk about later, right? There's actually kind of this keyword called #define, and basically what it means is it will have this symbol, right? This word or something, right? And it'll be associated with a number. And that'll actually end up being a way that we can have constants, because in macros, basically there's kind of a substitution rule where there's something that will go through your program and it'll say, okay, they have this value defined, right? Maybe they have, that I value, but it's defined using this kind of it's defined as a macro. And so basically, instead of creating a variable for it, it'll actually go and substitute in whatever number is being bound to I, for example 5 here, to all the places that I occurs in your program.